Hello, everybody. I'm very happy you could all attend today's webinar, where we will talk about some time-saving and unique features in FEM-Design. My name is Flavio Popescu. I am a structural engineer at StruSoft Denmark. And today I am joined by my colleagues Ciprian Zibea and Anders Nielsen. Today we will talk, as I said, about FEM-Design and Prefab Print. We will have a short introduction about StruSoft and our software in general. Then we will continue with the features in FEM-Design. Presented by me and Ciprian, we will show you some of our favorite features that make FEM-Design a unique software. And then Anders Nielsen will continue with a presentation of Prefab Print for prefab concrete elements. At the end, we can even have a Q&A session where you can come live with us and ask your questions, and we will be able to answer them in real time. You also have the option in your GoToWebinar window to type in your questions in the questions field during our presentations. We will do our best to answer all of your questions, and if by any chance we do not succeed, we will of course get back to you in an email after the webinar. Always feel free to contact us with any questions or queries regarding FEM-Design at any time. I would like to start by making a short presentation about StruSoft. Who is StruSoft and what do we do? Even though today we will focus on FEM-Design, our 3D finite element method software for structural calculations and design, we also have other software like WinStatic, for example, which handles single element calculation and design. BIM Energy for energy calculation and optimization in buildings. Impact, Precast, and Reinforcement for prefab concrete in factories. And Prestress for pre-stressed concrete beams and hollow core sections. If we take a look at StruSoft's history in a timeline, we can notice that it stretches from 1982 up till 2021. In 2020, we actually have founded our latest office in Helsinki, Finland. And today we are actually releasing the latest version of FEM-Design, FEM-Design 20. We will have some special webinars regarding the new features and improvements that have come with FEM-Design 20. Please keep an eye on our website, strusoft.com, and register for the upcoming webinars in the upcoming weeks. We have users around the world. As you can see on this map, there's a high concentration of our users in Scandinavia, but we have users around the world, including UK, in Europe, and some users in Asia and Africa, and also we have a couple of users in the US. StruSoft has offices around the world as well. The headquarters is in Malmö, Sweden, where we have 3 offices. We have 3 offices in Denmark. As I said, our latest office in Finland. We have offices in Estonia, Romania, India, Philippines, Hungary. Some general information about FEM-Design. FEM-Design is a good tool from a collaborative point of view. You can communicate with different software. One of these features is the ability to work with CAD references. So you can actually use CAD drawings and import them to FEM-Design and start building from the ground up. It's also possible to import 3D CAD drawings as well. FEM-Design has a good BIM integration, and there's a good communication with a lot of software like Graphisoft ArchiCAD, Tekla Structures, Revit, Dynamo, and Grasshopper. IFC import has been very much improved and is now available in FEM-Design 20. That is something to look forward to. FEM-Design can do a lot. Besides the analysis engine, where you can draw your structure, assign loads, manipulate the finite elements, mesh, and perform a load combination analysis and other types of analysis. You have the design modules, which are foundation design, concrete design, steel design, timber, and composite. For each of these design modules, you can get a detailed calculation report, verification, and design according to Eurocode. One special feature that makes FEM-Design unique is the crack section analysis for concrete design. FEM-Design performs a nonlinear analysis where it takes into account the reinforcement in the concrete and takes into account the cracks. Once a crack appears, the stiffness in the concrete is reduced and the calculation is performed again in an iterative process. You can also study the soil as a 3D finite element. This is a very accurate way of studying the soil together with the superstructure in comparison with a spring model or a bedding modulus model. The 3D soil gives the most realistic behavior of the soil. Let's take a look now at some FEM-Design features. I will start by showing you some of the features that I think makes FEM-Design unique. The first one is regarding concrete in the Reinforced Concrete Design tab. You have bar reinforcement, surface reinforcement, punching, and concealed bar reinforcement. With the concealed bar reinforcement, you are able to consider a strip of wall such as this as a reinforced concrete bar. And you are able to design it as a reinforced concrete bar instead of a shell wall and consider it as a bar. Let's have a look at how that works. First, I need to specify my concealed bars. For that, I choose my shell. And to make this easier for me, I will use some reference lines actually here. So again, I could select on concealed bar, I choose the shell, and I select the area which I want it to be considered as a bar. Now this strip of wall here will be considered as a bar, as the graphic suggests. We'll also make another one like this. Now I can perform a load combinations analysis and a design calculation. And all of the results will be displayed as for a bar instead of a concrete wall. This is just a different way to show the results. It is especially useful when wanting to deliver some sort of documentation to the producers. Now, if I go to my results, I can see that there is a new set of results called RC concealed bar. And I can see all the internal forces for those bars. Should be able to. Just need to design them first. So I can actually see some forces inside my bars. Again, this is a way to display the results as for a bar. It is the same calculations that are performed, it's just a different way of viewing the results. I also have some moments, and I have the utilization for these bars as a detailed result. And I will get the reinforcement calculation for that bar. This is a detailed calculation report which can be added to your documentation directly from FEM-Design. So again, it is the concealed bar feature in the RC design module. Another feature that I want to show you is regarding steel joints. This is a very nice feature that lets you define steel joints directly on your 3D steel structure. Perform a calculation and calculate the rotational stiffness of these joints. Again, I'm in the steel design tab and I have steel bar, steel shell model, steel joint, and steel bar fire design. I'm focusing on the steel joint. And here I have all of my joints already created, as I can see. I'll just select all of them and do a quick check. And if I go to results, I can see the utilization of these joints. I have a steel joint design module, which I can use. I go to manual design and I select one of these joints. I am transferred to the steel joint module where I can view my steel joint in 3D. And I can customize all of my parameters and components for this joint. End plate, top stiffener, bottom stiffener, diagonal stiffener if I have any, and then the haunch for the beam, end plate, bolts, and welds. I can see I have all of my parameters here. And my calculation in detail. If I scroll through this calculation report, I can see the stiffness calculation according to Eurocode. So I'll actually get a stiffness for this joint when I'm done with my modifications. I just click on finish and the modifications are applied. I just exit to my model. Then I have the stiffness tool here, and I can see all of the stiffness calculated for my joints. I can choose to apply it and run the calculation again with the accurate stiffness in the joints. That will give me a real result according to the rigidity of those joints. Let's move on. I will actually give word now to my colleague Ciprian. He has some features that he wants to show you. I'll just make him a presenter. Hello, Ciprian. Take it away.
Hello, guys. Hope everybody can hear me. Yeah, so without further ado, let's go into the first topic that I want to discuss with you today, which is connection forces. Like, we all know that FEM-Design is really good in what regards connection forces, and especially in precast structures, they really are handy, and they really save time. I taken here like 3 different cases. The first one is the edge connection between a wall element and the plate. Here in the second model, I used the line-to-line connection between 2 regions of plates at different heights. And in the third model, basically, as you see, I have like 2 steel profiles that intersect each other in the middle. And if I go to a physical representation of them, basically it's like this. Let's consider in reality. Now, even though the bar elements have this common point here, normally what a finite element software will do, it will connect and make a common point for both. But if I load one of them with, let's say, a linear load, both of them will will have the displacements in the same direction, because this is a common point. But if I use the point-to-point connection, we will see that I can make it free, and just one bar will deform, as it should be the realistic behavior. So if we go into the results tab, and we go to connection forces, we see that beside, let's say, the linear distribution of connection forces, FEM-Design also gives us directly the resultants, which is really handy for every engineer, because those are the results we actually use in our calculations when we design a particular connection. The same in the second case, assuming that this difference in height, of course, in reality here we will have something like a small wall, but assuming that we are not interested in that wall, we just want to see what are the connection forces. You can see that the line-to-line connection has already given me the resultants in all directions. And then last but not least, I forgot to show you how I load them. So sorry, this is the load approach that I used. Right, and for example, if we return now and we go to load combination and we do the displacements, we see that just one bar is being displaced because the common point is no longer common. By using the point-to-point connection, we can basically split those points and transform them into 2 separate points. Now, maybe you are asking yourself, okay, but how do I do that? Well, it's pretty easy. Of course, with the connections between, let's say, a plate as I have here and the wall, what I do, I go to edge connection. I just click the element, click the edge that I'm interested. And here we have it, like I can place it as fixed, hinged, free, or free totally. So yeah, I can play with the degrees of freedom. I can do, I can change the rigidity, change them to whatever value I feel confident as an engineer. But this is the most common one, the one that maybe all of us that were using FEM-Design has used at least once. The next two are a little bit more, let's say, less used. This is the line-to-line connection. And here, basically, you define it in the same way, like what type of connection do you want to have between the edges at different levels. And here is basically where the connection should be placed, in the middle between the two of them, maybe at the top or at the bottom. That's up to you. And then last but not least is the point connection, which again, in my case, it was free, but it can well aware be hinged or fixed, depending on the case and what you want to simulate. And of course, the reason why those are displayed like this is because I changed the physical alignment for them. So this is done easily, you know, like you just go to the bar and you click the physical alignment button, and then here you see the physical alignment is basically on the top part of the profile, and for the next one is on the bottom part. So yeah, this was connection forces. Now this is the simulation of Camber in FEM-Design. Now I taken this hollow core model approach. As you can see here, it's a same hollow core profile. Basically, those two hollow core slabs are with multiple panels each, are identical in all aspects except one, which is of course the camber. I used like a simplistic approach of supports, like having a hinge connection, a line hinge connection here, and simply support in the parallel direction. And I loaded both of them with the same load, but the difference is here in the Camber simulation by pre-stressing. Here you basically place this eccentricity and the total force per strand, and then FEM-Design will calculate in a separate load case the Camber simulation. Now, if you clicked this one, you will notice that when you go to loads, you have this Camber simulation load type, which you didn't have before. So in order to really simulate the Camber and to use it in your load combination, you will have to first define it here in load cases and then add it in your load combination tab as well. Now, if we go to analysis and we look, for example, first at load cases, I just want to see the Camber simulation, right? So the other one stays perfectly flat because it doesn't have any camber force, pre-stressing force. The other one, as we see here, it's already it has a pre-camber effect due to the pre-stressing behavior. Now, if we move forward to the load combination, basically I added on both of them the same load. while this one is going, it's bending towards this one. The pre-camber is still not yet totally consumed, so it still has a small pre-camber of 2.51 millimeters. Don't take these results as for granted. This was just with the presentation purpose. So yeah. So this is basically how you use the camber effect, and I guess this is about it. This feature, and the next feature that I would like to talk a little bit is the punching shear. Now, and different types of punching shear that we can use. So I just created this plate, and I played a little bit around with the different types of reinforcement, punching shear reinforcement that FEM-Design can apply. So in this case, this was a Pico punching shear reinforcement. This was a custom-made punching shear reinforcement. This one is with circular stirrups. Next one is, of course, with banded bars. The last one is with this special reinforcement, which is made in situ. Usually they bend the bars like this, and they just place them as a punching shear reinforcement. Now, of course, that if, for example, I want to check if whether this design was okay, it was not okay. Here it will show me that, you see, my shear force is much punching shear force is much higher than the required, so it's not okay, and it tells me that shear reinforcement should be extended. For the last three columns, I used an auto design feature, but it's still not okay. Mainly because I will have to increase the diameter that I had in my settings. So as soon as you defined everything okay in your either manual setting, or you can let FEM-Design do an automatic design of the elements, then it should be okay, and it will show you the degree in which your connection still has some reserve capacity, or as it was in my case, it's not okay. So basically this is how you perform this punching shear. Now, if I go here, what I wanted to show you is that FEM-Design automatically creates this refined mesh results in near the column, because otherwise we will have like unrealistic results. And this basically what it does, the peak smoothing function, it smoothens the peaks and the unrealistic results, because of course, as in every other finite element software, the bar elements are just line elements, and plates are just shell elements. So you can imagine that in reality, this bar is actually not a bar, it's a column maybe by half a meter by half a meter. So yeah, this is why FEM-Design automatically applies this, and it's very good because you don't have to bother with it anymore. Now the next feature that was maybe reminded by Flavio, but yeah, it wasn't even in the agenda, but I thought it's nice just to show you. I presented it in a previous webinar. It's about the 3D soil and the interaction with this superstructure. Now, as you can see, basically, if you didn't have the 3D soil functionality as I did here, You will have to define a bedding modulus to exchange the rigidity of the supports and so on and so forth. So long story short, for me, it was really easy to define this prism of soil, to define some soil layers, some underground water level, and then just run the analysis. And as you can see here, it showed me directly, okay, my building is going to rotate a little bit, is going to go more in depth into this area. So, and I get, of course, a more realistic results in my elements, so I can design them properly and accordingly. And again, last but not least, I wanted initially to talk a little bit about delta beam. I will not go in depth because we will have a new webinar with our colleagues from PICO planned soon, and we will talk more in detail about it. Also about our new composite module that will come it will be very good for this delta beam frame approach that PICO are using. So this is why I won't go into details now. But just as a reminder, the delta beam, if you go into the beam tab, you will see that here you have this delta, and basically you can select different sections and then do the analysis, and it will tell you if whether the section that you applied is good enough or you have to increase it or decrease it. All right, guys, then that was all from my side. If there are any questions, please just either write them directly here or send them to me by email. And as my colleague said, we will do our best to answer in the fastest time possible.
Thank you,
Flavio,
Cipriano.
yeah, switch please the presenter to Anders.
Anders, can you hear me?
Yes, thank you. Hello, everyone. So I'm going to talk about our new software, and I say new, but it is actually almost a year ago since the first release. Still, that's fairly new in comparison to some of our other softwares. This software is called Prefab Print, and for starters, you might want to know that Prefab Print is a tool to automatically generate a report of a concrete element building. And this is a report of the load takedown and the stability check. And the purpose of this report is that it is, first of all, it's easy to read. It has a uniform setup, and it provides a visual overview of the loads on each concrete element. If we consider the force distribution in FEM-Design, the default setting is the one called constant by element, and it gives us these sort of staircase looking forces in the connections between walls. So what Prefab Print does is that it converts this to either an elastic or plastic distribution, and you can choose which one of those you want to use. Also, recently we have developed a new optimized plastic solution if you choose the plastic force distribution, but we'll get to that. So the conversion is done by considering the edge connections, and Ciprian spoke a bit of the edge connections on walls and plates. Each edge connection has its own local coordinate system, like shown. The x-axis is along the edge, while the y direction is perpendicular to the edge. And to prevent that this new distribution, either the elastic or plastic distribution, will give us high values above, for example, openings in walls, we have decided to neglect areas that has a value of 10% less than the maximum value in that particular edge connection. Meaning, if we consider the forces in an edge connection and we find the maximum value, we neglect all other areas that has a force that is less than 10% of the maximum value. And I say neglect, but that's not entirely true, because we do consider these areas as beams, basically. So if they are positioned between two other areas, they are considered as a simply supported beam. And if they are at the end of the edge connection, it is considered as a cantilever beam. And the reactions of those beams are then applied to the neighboring areas, as you can see. And from here, we are able to determine the resultant force in each of these separated areas, and also the position of the resultant force. And from that position, we are able to create the elastic distribution or the plastic distribution. A very important feature to use in FEM-Design is the detach function, as shown here. This is very important, at least in Denmark, and I know there are other countries doing it like we do. So in Denmark, when we place two walls on top of each other, we don't want any tension between those walls if the wall above is about to overturn. So any tension should be taken in tensile anchors instead. To make sure this works properly, we use the detach function as shown, and I will show that live as well. The shear between two horizontal edges of two walls is calculated in the report by the formula 625, as you see. We only consider the friction part, which is the one you see here. So cohesion and the reinforcement is not applied. Just keep that in mind. So let's have a look at a model like this. This is a 6-story building. This is actually just a 2D wall. And Prefab Print works both for 2D and 3D. So as you can see, I've put in some edge connections here. Don't mind the language, it's in Danish. If we take a look at the stiffnesses used in the edges. So this is the one on the bottom. This is, you can see I've used the detach Y tension function. And what this does is that it converts the value up here into 0. But not only that, it also makes sure that any shear in this joint is only transferred in the compression zones. So there's no shear transfer between these two walls in the tension zones. If we don't use the detach function and we just put the value to 0, the shear will be transferred across the entire edge. If we look at the stiffnesses in the joint here, I want shear to be transferred across the entire edge here, so I don't use the detach function, but I do put the tension value to 0 in the y direction. And the y direction is perpendicular to the edge, remember that. So that is between these two walls. So no tension is transferred between these two walls, only compression. And I've put in a value of 20,000 in the x direction. And this is basically just a value. You can put in anything here. The higher the value, the more force will go into your joint. Okay. So let's run the analysis. One thing I didn't mention here, you see all these small dots. And these are actually also very important because now that I have said that these two walls can't transfer any tension between each other, FEM-Design is actually likely to do so still in the last node out here. And to prevent that from happening, we need these dots. So these are applied with this endpoint behavior. So basically I select the entire model, and then this is odd to some. Now I select all of the edges, and as I want to apply this to the whole model, I select the model again, and now I select all of the endpoints. There are 2 endpoints in each edge. So basically I select the model again, and I choose the separate endpoint from environment. Okay. Now they were applied, so there's no changes here. Also keep in mind that I apply these edge connections on both sides, so both on this wall and on this wall. This is not necessary to use FEM-Design in general, but this is necessary when we want to use the Prefab Print. Also, I forgot the loads. I have created a self-load with the structure plus structural dead load and a wind load. And this is also important how you apply these loads. So I've chosen to use a horizontal line load on the walls, as you can see here. And if we take a look at the one here, for example, you see I've moved it just a little bit. Because if the load was applied directly on the edge between these two walls, FEM-Design is not able to determine whether the force or the load is acting on this wall or this wall. So either you can choose to move them just slightly, as I've done, or you can use the assign load to structure. If you use this one, you just select the load and select the wall, and it turns green. So either of these two methods work. Yes, let's try to run the analysis. This is a non-linear analysis that I've chosen to use, and this is because I want to rely on the reactions and the forces that FEM-Design calculates for me. So this is FEM-Design doing the load takedown and the distribution of the loads. Okay. Now that I have run this this analysis, I can open up Prefab Print, and you can see it has noticed that I did run a calculation in FEM-Design, and it asked me to whether I want to load in this calculation, and I do. Tells me I have a utilization of 243%. And that's not good, but it's not terrible either, because if we do, sorry, you don't know this. This is Prefab Print, actually. And in the project information, I can type in information about my project. There's not a whole lot to do in Prefab Print. You just load in your model, and you basically you print out a report. In the calculation settings here, you also choose which code, Eurocode, you want to use. And here you can choose between the elastic or plastic distribution in our compression zones. In display model, I can actually see the model. I cannot do anything else in here though, so I just use this to know that, yes, I did in fact load in the correct model. And in settings for printing here, you choose the load combinations you want to be included in your report, and you also include tooltips and design checks. This is my recommendation, and I'll show you why. So let's try to print this report. It looks like this. Start off with an overview of the wall, or the model, basically. And then we see an instruction as to which symbols are used in the report. You see the paper size did change here. So this is not a print out friendly report. You're not supposed to print it out on physical paper. Also, a lot of informations are not shown on your report. They are hidden in tooltips, and that's why we want to include tooltips. So if I click on this wall element, you can see here the information about this particular wall. It has a unique name from FEM-Design, the geometry, center of gravity, self-weight, and the strength we have chosen also in FEM-Design. It is the dimension lines, as you can see here, are automatically applied. I can turn it off if I want. I can do that with everything. And the next page here you can see is the applied loads. So this is the wind load that I applied. Also, I can click on it. I can see how long it is, the coordinates, and the value. I can also see it over here. And if I click the button here, it points to where this one is acting. So scrolling down here, you can see the forces in the edge connections. So this is the reactions on each wall and the entire takedown of these loads. So I chose the elastic distribution, so I get a distribution like this. And you can see some green and yellow signs over here. So the green ones are obviously that everything is okay. In here it says compression is okay. Where do we have shear as well? We do here. So here it says compression is okay and sliding is also okay. And this is done accordingly to this formula, but only the friction part, remember that. So if we take a look at these yellow ones, it says break in sliding. So I need additional reinforcement here. I only lack 9.1 kilonewtons here. I might be able to find that in the cohesion part. If not, I can apply some reinforcement. But that is done manually. So the yellow signs tells you that you should be aware of the missing sliding capacity here. It can also turn red, this symbol, and if it is red, it's either because compression is not okay, or where was it? Or that we have exceeded the maximum value available for sliding capacity, which is this one. Yes, let's have a look at a 3D model as well. Sorry, no, not just yet, because there was also the plastic distribution here, and we also added an option to use plastic optimized solution here. And if we choose this, let's print out this. We don't rely on the results from FEM-Design anymore. If we choose this, Prefab Print generates a new distribution. And it does so based on an optimization algorithm. So it looks at all of the compression zones, and it has a capacity in there. And it will then move the loads around in the structure to try to find the lowest utilization possible. Still, each element has to be in equilibrium, though. That is, of course, necessary. If we were to apply a load-bearing capacity in our shear joints, in the vertical joints, that would also be taken into account. Also, any tension anchors, there's none in this model, but you can apply some, and you can limit them to a maximum force, and it will also optimize in that as well. So, for example, let's have a look at the 3D structure, because it also works with the 3D structure as well. In here, I have actually put in a plastic limit in the vertical joints here. It's 150 kilonewtons per meter. That's a maximum value I want in these joints. I don't know if I put in some here. No, we can do that afterwards. Now that I know beforehand that I want to use the plastic optimization algorithm to do the distribution of loads for me, I don't have to rely on the FEM-Design result. And therefore, I can run my analysis with a very, very high finite element mesh like this. Also, if I go to analysis, I can choose the standard element instead of the fine, which is standard. And I don't have to run the calculation as a nonlinear analysis anymore. I can run it as a linear analysis. So this is much faster, as you can see. So here we have the 3D model. So it splits up the walls in 2D as shown, and it gives us a report of each of those walls. If we take a look at the grid line A here, you can see that we have forces here that's 14.5 kilonewtons here. And that is, if we take a look at our model, that was in the grid line A, as you can see. And I should say that the horizontal force here is acting in this direction. So this wall here will act as a stabilizing. It will try to stabilize the wall here when it's trying to overturn in this direction. And that's the force you see here, 14.5 down here. So that's A. If we take, sorry, that's 1. If we take a look at 1 here, you can see we have 14.5 as well here in the upper direction. We also see that the compression zone, for example, here, where we have a small lintel above this opening, it is it's 48 kilonewtons per meter. Now, this isn't much, but perhaps it's too much. I don't know. If we would like to reduce the force on this lintel here, on this beam, we can do so by limiting the plastic capacity in this area. So to do that, we use the break function over here. I choose the edge connection here. If I position my mouse here and hold down the shift, I get a helping guideline here that I can snap to, like this. Okay. So I did split up my edge connection here. Now I can choose this and I can put in a plastic limit, let's say 20 kilonewtons per meter. So this is now my load bearing capacity of my beam, basically. So let's try to run it again. And as you can see, it has now removed the force here. So the optimization algorithm actually determined that it is better not to put any load in this particular area at all. It moves all of the load over here. So this gives us a lower utilization overall for our structure. Any sliding issues, as you saw on the first page here, yeah, we did run the plastic optimization as well on the exact same wall. It doesn't optimize to find the lowest value in sliding. It tries to not exceed 100%. So if any area is more than 100% utilized in sliding, it moves just enough so that the utilization is exactly 100%. Still, it is only according to the friction capacity. And of course, this works as well for larger buildings, as you can see, for example, this one. And I can open the report. You can see that it generates from here. It does take a bit too much time to print this live. So I've done it like this instead. But as you can see, this is the model. And here we have all our walls in all the load combinations that I've created. Yes, okay, that was it for me. Flavio, do you take over here?
Yes, thank you, Anders. You can keep in touch with our schedule for the webinars. We do regular webinars. If you go to StruSoft.com and go to FEM-Design, you will see that there are webinars and trainings section. And here are all the scheduled ones for FEM-Design. So you just click on one. The next one we have is on the 11th. It will be a first introduction to the FEM-Design 20 new features. So I really recommend you sign up and watch it. It will be very interesting. Also, here on our website is also where you can apply for a trial. If you're not using FEM-Design yet, just go to the FEM-Design page and click on Get Started Now and apply for a trial right here. You fill out this form and then click Submit. Another way to stay in touch with us is through our YouTube channel, StruSoft Official. And just click subscribe, and here is where you can find all of our video material regarding FEM-Design. Thank you again, everybody, for attending. Thank you, Anas and Ciprian, for making this webinar happen. And I wish you all a great rest of the day and happy modeling in FEM-Design.